Imagine you're looking for a word in a dictionary. You don't start at page 1 and flip through every single page. You open it near the middle, see if you've gone too far or not far enough, and jump again. That's it. That's the entire idea behind one of the most important algorithms in computer science: binary search. By the end of this video, you'll not only understand how it works, you'll understand why it works, where it breaks, and how to code it without off-by-one bugs ever again. Because the array is sorted, we can be clever. Pick the middle element. Compare it to the target. If the middle element is the target, done. If the middle element is smaller than the target, if it exists, must be in the right half. We can completely discard the left half. If the middle element is larger, the target must be in the left half. Discard the right half. Each comparison eliminates half of the remaining elements. That's why it's so fast. This is logarithmic time, O of log n, instead of linear time, O of n. Let's trace through it. Array: 2, 5, 8, 12, 16, 23, 38, 56, 72, 91. We're searching for days. We track 2 pointers, left at index 0, right at index 9. Step 1. Middle index equals left plus right divided by 2. That's 0 plus 9 divided by 2, which is 4. Element at index 4 is 16. Target is 23, which is bigger than 16. So we discard everything from index 0 to 4. New left equals 5. Step 2. Left is 5, right is 9. Middle equals 5 plus 9 divided by 2, which is 7. Element at index 7 is 56. Target 23 is smaller than 56. Discard index 7 to 9. New right equals 6. Step 3. Left is 5, right is 6. Middle equals 5 plus 6 divided by 2, which is 5. Element at index 5 is 23. That's our target. Return index 5. 3 comparisons, 10 elements. That's the power of having. Notice the loop condition. Left less than or equal to right, not left less than right. This matters. If left equals right, there's still one element left to check. Get this wrong, and you'll miss valid answers. Also notice, when we move left or right, we go to mid plus 1 or mid minus 1, never just mid. If you forget the plus 1 or minus 1, you risk an infinite loop because the search space never shrinks. These two details are where almost every binary search bug comes from. If your code is looping forever or returning wrong answers, check these first. Time complexity, O of log n. Every step halves the search space, so for an element, it takes roughly log base 2 of n steps. For 1,000,000 elements, that's about 20 steps. For 1,000,000,000, about 30. Space complexity, O of 1 for this iterative version. We're just tracking 2 pointers, no extra memory that grows with input size. Binary search isn't just for searching arrays. It shows up in finding boundaries in monotonic functions, searching answer spaces in optimization problems, and is a core building block in tree and graph algorithms. The pattern to remember: if your search space is sorted or has a monotonic property where you can definitively rule out half, binary search is on the table. Next time you see a sorted array problem, your first thought should be, can I cut this in half? If this helped, subscribe. We're building out the full DSA roadmap one algorithm at a time.